When viewing a sample made with pigments, the color seen is a result of the interaction between the underlying surface or substrate of the sample, the thickness of the film that is applied, and the way in which this film is applied. The film thickness must be uniform in order to achieve accurate results in matching samples. This can be most clearly seen when working with ink samples. These samples represent the same ink drawn down over the same surface, but at different thicknesses. Because the thickness of the ink film has an effect on the amount of light that reaches the substrate and is scattered back to the eye, an observer sees differences in film thickness as differences in color. In an ink sample, the film is applied to the substrate by drawing it down either mechanically or by hand with an applicator. The resulting film thickness depends on the speed and the pressure of the applicator, as well as the viscosity of the ink as the film is applied. If a wire applicator bar is used, the gauge of the wire affects the amount of film deposited. A spectrophotometer does not directly recognize that differences in color may be due to differences in thickness. It's therefore necessary that film thickness be controlled, especially when presenting samples that are not opaque to the system.
Once when I was working in a paint plant that made industrial paints, I noted that when they sprayed out a test panel to illustrate where the batch was, they weren't very careful about the film thickness. So with the General Superintendent's permission, we took a batch and sprayed out a large number of panels, and then selected a few of these and compared them to the standard. Well, in fact, the standard was the production batch. We asked all the people involved what kind of adjustment they would make, and they said that you overshot in black pigment, you have to come back with a white add. We measured the samples and asked the computer what adjustment it would recommend. It said you overshot in black and have to come back with a 30% white add. And since there was 1,000 pounds of titanium dioxide in the batch, it meant that we should add 300 pounds of TiO2. Well, since we were comparing the batch to itself, the difference was not due to any difference in pigment. It was due to the difference in film thickness. Very often, a lot of pigment is wasted because of poor thickness control.
Ink is, by its very nature, almost never totally opaque. It almost never hides the substrate totally, and therefore the substrate becomes an integral part of ink color. Not only the color of the substrate, but its absorbency and gloss affect the color. So an ink, when it is matched, it must be printed or proofed on the same substrate, or at least a very similar one to the one the customer is going to use in his plant. Otherwise, color matching will never be correct.
Different substrates have different characteristics which can affect sample appearance and the accuracy of color measurement. One characteristic is the color of the substrate. In this example, one substrate is magenta and the other is white. The effect of different color substrates on the appearance of a sample can be seen as a green ink is drawn down over both substrates. Although the same color ink is used, the appearance of the two samples is noticeably different. The absorbency of the substrate is another important factor. If the substrate does not absorb the colorant evenly, the color of the sample will not be uniform. These samples show the result of an ink film applied to several substrates. These differences in the color and absorbency of the substrate cause the samples to look different. When making samples in the lab, the substrate selected should ideally be representative of the material used in the final product.
The substrate greatly affects the appearance of color, and let me give you a few examples. The gloss of the fabric, if you're using a polyester or nylon glossy fabric, that will affect your color, especially if you're matching to something that is a velour or a yarn sample. We see a variation in color, especially when you're looking at velour fabrics, carpeting. The directionality of the pile greatly affects the appearance of the color. Also, if a substrate is dirty or yellowed, that will also affect the color that you see once you get your final product. So the preparation of the substrate is very important.
The process by which colorant becomes part of the sample can have a significant effect on the sample's appearance. In paint and ink applications, there are several ways a film can be drawn down over a substrate to make a sample in the lab. Some applicators are used to draw down a film by hand. Other types of applicators are electromechanical. An electromechanical applicator generally provides the most consistent results. Because different applicators lay down different film thicknesses, the applicator chosen should correlate with the type used in production and offer the greatest degree of repeatability.
One can also use small hand-driven laboratory presses, which are very popular in the ink industry in many laboratories. Unfortunately, the key parameter of speed is not controlled via a mechanical device, and this can lead to substantial color differences during proofing.
When batch dyeing textiles, the factors of time, temperature, and pH, the acidity or alkalinity of the water, all have an effect on the final result. Controlling these variables will help to ensure an acceptable degree of repeatability and reproducibility. A key objective in all lab work is to get results that correlate with actual production processes. This is often difficult because of the differences between the equipment used in production and the equipment available in the lab.
Repeatability of a process is very, very important to lab-to-plant correlations. In setting up these correlations, what I recommend is that you allow a technician to mix up the same dye formula 3 days on 3 separate occasions and prepare those in the same method that you prepare any dye formula, whether it's exhaust dyeing, continuous dyeing, or printing. What you want to do is to ensure that on those 3 days, those 3 dye formulas give you the exact same shade. This allows you to see if your process is repeatable. If it is not repeatable, then maybe you need to go back to the drawing board and see what machine parameters need to be altered, how closely your water coming into the plant is monitored, and all of the variables that affect the color, the final color of your dyeing. Maybe you need to go back and adjust those, monitor them more closely, and see if your process can be changed to become a repeatable process.
There are several types of problems that can occur when you have laboratory-to-plant correlations. One has to do with just the simple size of the equipment that's run in the laboratory versus the equipment that's run in the plant. In our case, we make a lot of colorants. In the laboratory, we might make a quart sample. In the plant, we'll be making 800 to 1,200 gallons. And a lot of the problems that you run into have a lot to do with cooling type problems. In the laboratory, it's easy to keep a lab mill cooled, water cooled. In the plant, sometimes you have to refrigerate the mill to make sure that the operating temperatures are appropriate. The problems that you run into if the operating temperatures get too high is that the viscosity tends to increase on the colorant, and you don't get the kind of strength development that you'd like to get. You might be shooting for 100% with one pass through a sand mill, and maybe you'll get 85% or 65% or something like that. And that's directly related to the fact that you're working with different quantities, and you can't keep the product as cool as you'd like to cool it as you process it through the particular mill.
We have found that by tailoring our laboratory mixing procedures, we are able to best correlate to the products that we make on the production floor. We have in our industry 2 distinctively different forms of coloring. The powder form is known as dry color, and when it's prepared, it's mixed in a very low shear type of mixing operation, and the pigments do not develop their full strength. And we found it very helpful in doing color matching and correlating to the dry color side of the business to establish a low shear set of standards for each of the pigments we have in our business. On the other hand, the pellet concentrates are made on high shear mixing equipment. There are several forms of melt processing used by the industry, and each of these will generally create a different degree of color development.
One of the biggest sources of problems in lab to production correlation is pH. pH control of the water varies from day to day as it comes into your plant. You may have 6.5 on Monday and 6.2 on Wednesday, and if you're trying to repeat a color from day to day and the pH changes, you will see a significant difference in the color. So therefore, if you monitor the pH and check the pH of each dye bath as it's mixed, you should get repeatable formulas from day to day.
The important difference in correlation is between the customer's plant and between our OK. We may match a sample the customer has given us, but if it isn't the same film thickness as we produce in the laboratory, then even if the color matches, it won't in production. So the key component in matching color in an ink laboratory is to have a feeling or knowledge of what film thickness the customer is ultimately going to produce in his equipment.
One of the other problems that can occur is the actual correlation of the equipment from a research laboratory to a manufacturing site. In the trade sales portion of the coatings industry, most products are produced on what are known as high-speed dispersers. And the actual work on a high-speed disperser is done at the tip of the blade. So what we've done is determined what the tip speed is of the blades in our manufacturing facility, and then make sure that our laboratory mills correlate perfectly, or we can correlate them perfectly, so that we generate the same kind of energy out of each of the mills. And usually it's easier to identify what's occurring in the plant and then correlate that to the laboratory rather than do the work in the laboratory and then try to force it into the plant.
Another source of variation from the lab to the plant is the machine parameters. In the lab, all of the controls usually are automated. You can control such things as process time, temperature, speed of the machine. And when you take that formula and run it out in the plant, your speed, temperature, and process time all may vary slightly from the lab machines. This can create a significant difference in color also. So it helps if you can calibrate your machines and get them in sync with one another to where when you do set for a specific process time, speed, and temperature, that you see the same from lab to production.
Repeatability and reproducibility in both the lab and plant are maintained through the quality control of the raw materials. The ability to match colors ultimately depends on the use of consistent raw materials in production formulas. When the raw material is a colorant, the strength and the hue of the colorant need to be consistent from one lot to another. A computerized color matching system can evaluate each incoming batch of colorant based on its spectral curve. Differences in strength between the incoming batch and the standard can be measured, and the system can calculate how the concentration of the incoming colorant should be adjusted to match the target color. If the hue of the batch differs, however, adjusting the concentration will not result in the proper color. This computer output shows a delta H, the difference in hue, between the standard and the incoming batch of 1.67 units. An acceptable match may therefore not be possible by directly substituting the new material. To help ensure that incoming colorants are acceptable, they should be checked against standards using predetermined specifications or tolerances. These tolerances are best established through close cooperation with suppliers.
If you don't look at your incoming raw materials, you are creating a complex and time-consuming problem by not having control over your own process. And this holds true whether you do visual matching or automated color matching.
In all industrial color applications, there are several places where color is measured and quality control checks performed. Typically, quality checks are made when the raw materials are received, when a new color is formulated in the lab, and when the production batch is completed. Upon delivery, the raw materials should be checked before they are distributed to the lab and production. Colorants should be checked for strength and hue. Components such as resins, additives, and substrates should be evaluated as well because they also contribute to the color of the final product.
Raw material control and incoming testing occurs at one facility, say a central type facility where there's a large analytical laboratory or research and development laboratory, and the branch plants sometimes will not have the same capability. And you need to be very careful to make sure that all raw materials that come into your organization, whether they come into a branch facility or to your main facility, are tested to make sure that they produce the same result time after time.
The second color check is made when a new color match is formulated in the lab. Once approved, the formula is submitted to production. The third color check is typically made when the production batch is completed or near completion. In addition to these three evaluation points, instrumental color control can also be a helpful evaluation tool at the other stages of sample preparation and production. One such stage is the creation of a formula. In the lab, the formula can be created instrumentally. Preparing a sample in the lab is another stage where the system can be used. Here, the system can serve as a tool to evaluate the repeatability of the procedures used in sample preparation. This includes the evaluation of techniques for weighing and dispensing, mixing and sampling, curing and drying, and application. Instrumental color control can continue to be helpful in production. A formula is usually developed for a specific set of equipment and raw materials. Changes in equipment or raw materials often require an adjustment to the formula. The system can be used to make adjustments before processing begins. Instrumental color control is a useful tool when the batch is processed. Adjustments to a range of variables in processing can be made to control color uniformity within a batch. This is done by sampling the batch at regular points and evaluating the color instrumentally. There must be a correlation between the results achieved in the lab and those achieved in production. In some cases, there may also need to be a correlation between the results achieved in production and those of the end user. The system can be used to develop correlation factors. When making instrumental evaluations, numerical tolerances for color acceptability exist at each evaluation point. These tolerances should be appropriate for the application and must fall within the repeatability limits that the operation is capable of achieving.
We have to have a tolerance for color just like any other element of the product that you manufacture. The tolerance will depend on the end use. If you're going to make a bar 12 inches long and that bar is going to be used as a window weight, the tolerance may be 12 inches plus or minus 2 inches. On the other hand, if it's going to be used for a precision instrument, the tolerance may be 12 inches plus or minus 1,000. In the area of color, if we're making blue laundry tags, as long as they're blue, that's usually sufficient. But if we were making a highly visible exterior component in an automobile, we would have a much tighter tolerance. You cannot have a tolerance of a half a unit for a paint if you can't make two samples of the same paint within 1 unit. If you got to a half a unit, it's just by luck. So the repeatability and reproducibility information that you acquire will tell you when to quit.
We need to set our standards. We need to make sure that our standards can be reproduced, but we need to make sure that our standards are good. Sometimes our research and development people have done a lot of work, but their balances weren't calibrated properly, or their spectrophotometers weren't calibrated properly. And then when you get into manufacturing, who calibrates the equipment in manufacturing? Who checks the meters that you meter your materials in with? Who guarantees that things are clean? We've taken too many shortcuts in our desires to get things out quickly, and we need to get back to doing things right and doing them right the first time.